But okay, now that everybody got their food, we can get started. It's my pleasure to introduce Mark Zhao, our faculty candidate. Mark comes to us from Stanford, I guess electrical engineering. He's a PhD candidate, finishing up his PhD, and he'll tell us about machine learning pipelines and what to do with them.
Yeah, thank you so much for the warm introduction. It's such a great honor to be here. You know, talk about my work on building systems for scalable ML pipelines. Feel free to stop me if you have any questions, and I'll keep things generally on track. Also, apologies about the thing floating over the title. So if something is confusing, feel free to stop me and ask what that says. So many of you have probably seen this figure before or something like it, right? And that's because us systems people love to use this image. And what this is showing is that the amount of compute on the y-axis needed to train the state of our ML models is rapidly growing over time, even outpacing trends like Moore's law. And we like to use this because we can say that, well, if we're able to build systems with more GPUs, faster GPUs, that enables us to train larger and more capable models. But I want you to think about what's missing from this image. What are we presenting here? And to give you a hint, here's one word, data, which should be over there, but we ignore that. To train increasingly larger models, we need more data, right? These data sets on top of the compute have also been growing rapidly. We've seen an increase of the data set sizes, again, 3 times year over year, as shown on this graph here. And furthermore, we need this data faster. Companies like Meta, Google, Microsoft are deploying millions and millions of GPUs in these data center scale training clusters in order to keep up with the computational demand that these models need. So if we actually want to use these GPUs, we need to process and ingest all of these data sets fast enough to feed the millions of GPUs consuming this data. So in summary, to meet this data demand, modern ML deployments require scalable data pipelines. And my key message today is this. There's one point I want to get across is that if we want to continue scaling our ML capabilities or ML systems, we need to focus on collectively improving all of the different systems throughout the ML pipeline, not only just the GPUs or the disk components. So to give you a bit more to work with here, let me start with an example of a real world ML deployment, namely a recommendation system. And why recommendation systems? Well, if you all have ever used products or apps like YouTube or Instagram, then you've used a recommendation system. And so these systems are used under the hood to suggest new and relevant content that fit your interests. And as a result of their prevalence, their kind of ubiquity, these systems need to handle massive amounts of scale. They're taking in requests from billions of daily active users. And at the same time, to continue improving the quality of these recommendations, these applications, they're adopting all of the advanced techniques out there, generative models, agents, you name it. So let's go one layer deeper to see what goes on under the hood here. And to start off, let's look at the inference side of things. So on the inference side, when a user, let's say Audi, who has some interest, uses an app like Instagram, well, Instagram is calling this inference system under the hood. And what this system needs to do is it needs to find the best post to show Audi. The tricky part here is that it needs to wade through billions and billions of options of what to show her. And it needs to return a result instantly within a few milliseconds to give us that response that we're used to. On top of this, as I mentioned, we're dealing with massive scale here. We need to handle millions of concurrent users. So what's deployed in production in the real world is not just one component, one system. It's this pipeline with many specialized data systems, like feature stores, vector databases, DBMSs, that work alongside inference components, accelerators running a diverse set of models, like embedding models or deep learning recommendation models. And all of these different components throughout this pipeline work together to take loads of items, find the best one to show value instantly. But that's not the whole story. We also have to continuously train and improve these models that are then deployed back into this inference pipeline. So like with the inference side of things, we have a training system, and the training system takes these real world interactions, for example, Ellie liking a post. And the goal of this system is to, well, train a better model that's deployed back out into production. Again, there's a few tricky parts here. The first thing is that these models are massive, and of course, accordingly, their data sets are massive. We're dealing with hundreds and hundreds of petabytes of data that this system needs to manage. And on top of this, we're not training one model. We're typically running hundreds of different concurrent training jobs, doing things like hyperparameter search. We're targeting different types of models throughout this entire pipeline. And all of them are running on these data center scale clusters. And specifically, these data center scale clusters supply the computational resources necessary to train all of these different models. We're talking about tens, if even hundreds of thousands of GPUs. And again, these GPUs need data, right? These clusters are ingesting these data sets at tens, if not more, terabytes per second within a data set. So just like the inference pipeline, we need a training pipeline as well. And this training pipeline similarly has dedicated scalable systems that take, again, this raw data, engineer it into data sets, store these massive data sets, and then for each training job, process data throughout the lifetime of the training job to generate tensors, which go into the GPUs. And of course, the GPUs train the final model that's deployed back into production. So to circle back to the high level picture, what's the point of all of this, right? And I hope you've seen that, well, real world ML deployments require these complex data pipelines. And in this talk specifically, I'll focus on the training pipeline. And I'll show you how we build systems that manage these massive and growing data sets to feed these data center scale massive training clusters in the real world. And I'll do so by walking through 3 steps. First, I'll show you, well, how do we build these scalable data systems to keep up with the storage and the processing and ingestion demand needed by these modern training jobs. Then, because scalability is not just enough by itself, I'll show why we need to optimize the efficiency of these systems as well. And I'll walk through several examples of optimizations that I deployed in Meta's training fleet. And then finally, I'll present a framework that makes deploying these efficiency optimizations effortless, especially across a very diverse set of data workloads. So my research has also addressed a lot of other challenges in the entire ML lifecycle, which unfortunately I won't have time to discuss today. That's supposed to say systems for machine learning pipelines. I built efficient tiered storage systems that can efficiently deploy these models for real world applications. I built efficient tiered storage systems that are deployed at Meta to store these massive ML data sets. And then once these models are trained, I built systems that can efficiently deploy these models for real world applications like video analytics pipelines. And then finally, I've worked on the hardware and software infrastructure that underpin and supports all of these different pipelines, ensuring that they're not only more scalable, but because these are production workloads, they're also more secure and resilient as well. Of course, I'm happy to talk about any of these works, but for now, let me circle back and come to the training data pipeline.
It's a good question before we, so it was a right mental picture what you're saying.
Yeah.
So how often is this training pipeline run? Is it sort of done every day? Is it every hour? Is it interactive as soon as data arrives? What should I have in mind?
So all of the above. So we can think of this first data training step, which takes raw logs, raw real world observations as kind of a batch offline job. So this is a kind of a write once job every few hours or every day that generates kind of a new partition of your data set for the events that occurred over the past day. So these are kind of cron-like jobs. But then once we have the data sets generated, every time we run a training job, and so this happens hundreds, thousands of times a day, we have to do kind of a last mile processing operations, and these run throughout the lifetime of the training job. So there's more processing that's done during the lifetime of the training job to transform these data sets into tensors, which the GPUs will prepare.
Okay, so the last mile part that you're talking about,
Yes.
it seems to me that it's not like model learning, but maybe slight amount of refinement to the model, not necessarily, because are you learning a massively large thousands of different models
Sorry,
on the data set several times a day?
so this last mile pre-processing stuff, think of it like a PyTorch data loader, where you're taking raw bytes on disk and doing a few more data augmentations or transformations to turn it into a
So
tensor.
much simpler, right? It's much simpler than the complete model learning.
Well, it works alongside the model learning. So the GPUs are training the model. So these are like deep learning model or DNNs. And this is just, this pre-processing part gets the data ready so that the GPUs can train the model. So it's working alongside the actual training job, if that makes sense. Yeah. So there's no necessary learning happening here. It's more the transformations and data processing.
Got it.
Okay. Any other questions? Cool. So let me start off by going a bit deeper into first, again, how do we build these scalable systems to store these massive amounts of data? And specifically, I'll focus on these recommendation pipelines. And this comes from my work published in ISCA in 2022. And let me come back to this high level ML data pipeline, which looks like this. We again have these raw observations from real world systems. And the goal of the ML data pipeline is to take this raw data, which, as I mentioned, is continuously generated, and transform that into tensors for each training job to feed into your GPUs, which train final model. Okay. Feel free to ask me if that doesn't make sense. Cool. So if you've ever trained a model before, you might ask, well, why can't we do all of this locally? If we are running something like ImageNav, we'll spin up a server on Amazon EC2, and we'll download this data set to our local disk. Then we'll write a PyTorch data loader script or some Python script that processes this data using the host CPU, and then that will generate your tensors, which feed into your GPUs, which train the final model, right? And the answer to this is data demands. Production data demands are enormous. Specifically, what you can see here on the bottom left is 3 production recommendation model datasets at Meta. And these datasets are tens, if not by now hundreds of petabytes large, and that just simply doesn't fit on a local disk. Secondly, your data processing bandwidth demands are enormous. What I'm showing in the middle are for the 3 recommendation model training jobs, the amount of bandwidth demands and the units of CPU sockets or CPU servers that you need to do this data processing to keep up with the demands of a typical 8 GPU training node, right? So why I'm showing you this is that if we look at a typical something like NVIDIA DGX, which might have 2 or 4 sockets, that's not enough processing resources to feed your GPUs compared to some of these models which need dozens of these sockets to feed your GPUs. So what this means is that if there's not sufficient resources upstream of your expensive accelerators, all of your accelerators are just stalled waiting for data to come in, and it's crippling your training throughput, underutilizing all of your expensive compute resources, right? So the one way that we can address this is to rely on dedicated distributed systems to manage all this data. So for example, at Meta, we take this continuous stream of raw data, and then we, as I mentioned before, we run kind of these offline batch data engineering jobs, which generate these massive data sets. And so every hour or every day, we're continuously sending a new partition of this data set into a distributed, dedicated file system that we built called Tectonic Shift. And this is presented in my ETC paper. Happy to talk more about that, but I'm not going to go into super ton details here. And then to keep up with the demands of each training job, we built and deployed a dedicated pre-processing service called DPP, which is presented in this ISCA paper. And the goal of DPP is to continuously perform this data processing throughout the lifetime of the training job to generate the tensors to feed to GPUs. And of course, the GPUs train the final model. So the benefit of doing all of this disaggregation, which is where up there, is that by disaggregating all of these components, storage, pre-processing, we're able to scale them out to meet the demands of the GPU. So if we have a bunch of GPUs that need some amount of throughput in terms of batches of data per second, well, we can take this DPP pre-processing tier and allocate enough CPU resources to it to generate enough batches per second to feed the GPUs. And similarly, we can allocate enough storage resources, disks, to have enough IOPS to feed the rest of this pipeline, as well as to store these massive data sets themselves. This is great because it eliminates these bottlenecks, which are underutilizing all of our accelerators, but this comes with a trade-off, which is cost. We're just throwing resources at the problem here, right? So what this graph is showing is a breakdown across the 3 recommendation models of the amount of infrastructure resources in Meta's data centers needed to perform the data storage, data pre-processing, and then training in red for this entire pipeline. So as you can see here, a lot of the pipelines at Meta require more resources for these data systems than the actual GPUs themselves. And the demands for storage and ingestion are also rapidly growing year over year. So these different components, storage pre-processing, are really limiting the scalability of your overall entire training infrastructure in the real world. So if we want to build scalable ML systems, that requires building efficient data systems as well. And next, I want to talk about how we can optimize the efficiency of these systems. But before that, any questions? Yeah.
So the DPP work was largely in looking at trying to understand the limits at each step of how much can be pushed into how fast you can push things into the next step. Am I right?
Yeah,
So it was
yeah.
more of a study which looked at the evaluation of if I increase
Yes.
the data pre-processing
Yes.
pipeline, how much would it help with the rest of the steps, and to come up with some kind of recommendation or the recommendation, not in the recommendation.
Sure,
it's
yeah,
consent,
suggestions,
of
research problems, yes.
how much you need to scale up at each level. Would that be fair?
Yeah, I mean, there's a few goals that we have here. First is to show that we need to care about all these different components. B, exactly as you said, how much do we need to scale out each of these components in order to meet the demands of these jobs? And then, as I'll talk about in a second, how do we, after we've kind of done what you're saying, match the demands of each of these components, how do we use fewer resources? How do we optimize the efficiency? And that's where a lot of our
That's
research.
the next problem.
Yeah, exactly. Cool. So to start talking about this idea of optimization or efficiency improvements, you might have heard of this term called Gestalt before, which is that's supposed to be up there. Typically, Gestalt is used in design, and it means that the whole of something is greater than the sum of its parts. And well, my approach in building these efficient systems is what I like to call Gestalt optimization. And the idea here is that we're able to take individual systems optimizations and have them synergize together, work alongside each other to achieve greater optimizations throughout the entire pipeline. And to illustrate this, I'll walk you through 2 examples of these, how we apply these optimizations. And again, I'll start with an example from this paper. And so we're going to think of this as 3 steps. And step 1 here is to understand the application. And so these recommendation data sets, dive a bit deeper, kind of look like this. They're tabular data sets where we have this features column, which stores features which describe each user's interests. So for example, there's tens of thousands of these features stored in these lists of integers, which, for example, describe Alice's last inline posts. Right? On top of this, because there's billions of users, we have billions of samples. So these data sets, as I mentioned at the start, are massive. So understanding what this workflow looks like, what these tabular recommendation data sets look like, step 2 is to take that information and how ML training jobs applications use these data sets and distill a system insight from our observations. So that's step 2. And our system insight here is that, well, if we look at how ML training jobs read this data set, they actually perform a filter on this features column. They read a subset of the features available in this data set. And on top of this, they tend to collectively favor certain features over others. And what this means for our system, how this impacts our system is, if we take a look at our storage tier, we can see that a majority of storage IOPS, over around 80% of our storage IOPS, come from a minority of the bytes on disk, around 40% of the bytes on disk. And so there's this hot subset of data within our storage layer that's really read a lot by these training jobs. So taking that into account, step 3 is to, okay, let's deploy these synergistic optimizations throughout our entire pipeline to leverage this insight. And specifically, let's focus on this interaction between the storage tier and the pre-processing tier. To give you a sense of how we store these data sets, these tabular data sets are stored in columnar files. If you've ever heard of Apache Parquet or Bork, it's these types of files. And within these files, well, these features, the keys and values of all of these features, remember there's tens of thousands of these, are kind of interspersed together on disk, right? All the values across all these different features are interleaved together. And what this means is that if we want a training job, or if a training job wants to read a subset of features, for example, A and D here, well, it needs to read the entire set of rows for a batch from disk, reconstruct those rows in memory, and then for the features that it doesn't want, B, C, E, it just simply drops that data after reading it. And so, it just takes the data that it does want and continues to pre-process that. So you can see that this obviously wastes a lot of storage, network, data ingestion resources spent operating on data that's just unused. So our first optimization to try to address this problem is this idea of feature flattening. And let's apply that here in the storage layer. And specifically, what we'll do is within these files, we'll add a bit of extra metadata and rearrange how these features are stored so that all the values for a given feature, for example, A, is stored contiguously on disk, right? We're not interleaving all of the values anymore. And what this allows us to do is that now, when these pre-processing workers want to read specific features, they're able to do so with individual precise read operations or seeks to exactly the data that they want. So this is great because we read less data. We don't overread data anymore. And that allows us to improve the pre-processing worker throughput. But these are spinning disks, right? That's horrible. Any extra seeks is horrible for your disk IOPS. And adding these additional seeks cripples your storage throughput by around 97%. So let's try to address this problem that arises now in the pre-processing layer using this idea of merged reads. So here, this idea of merged reads is if we want to read features A and D, and there's data in between these two features, let's just go ahead and fetch all of this data in one disk seek, right? Let's go back to maybe overreading some data so that we reduce the amount of disk seeks. And the benefit of that is, okay, we get fewer disk seeks, so we eliminate these storage overheads. But you're obviously asking, okay, now we're kind of back to square one. We're overreading data again and just throwing it away. So what's really the point of all of this? If you bear with me for one more technique here, add a third technique called feature reordering when we actually generate these data sets. And this feature reordering optimization takes the insight where you can do kind of offline data analytics to figure out which features these training jobs like to read together. So we can run analytics jobs over all these training jobs to figure out how these training jobs like to batch features together. And so let's suppose that we know from this analysis that A and D are commonly read together. Well, let's just reorder them when we generate these data sets so that we write them together on disk. And now you can see the benefit of this, right? When we read A and D, we can do so with one disk seek and get exactly the data that we want. And so hopefully you've seen this idea of synergy here, where by combining all these different techniques across the entire pipeline, as opposed to just isolating optimizations in one system, they're able to synergize together, and we're able to improve 84% higher storage efficiency. We're able to almost double pre-processing efficiency. And the great part about all of this is all of these techniques are deployed into production across Meta's training fleets. Yeah.
What was, I didn't get that part. So are you doing a row-oriented representation or are you doing a column or what kind of data representation storage model do you have in mind?
These are columnar files.
So columnar file. So is it the case that one column is stored as separate file individually?
They're stored as separate contiguous byte strings within one file. So the baseline was that,
No, it's paginated, right? So does each page, so what basically have attributes of all different attributes, or they have only, is it batch-oriented model that you've got in mind?
so think of Parquet, right? We have row groups which store a few thousand rows inside a chunk of data.
So that's facts, basically, that's facts.
Yeah.
That's what
Yeah,
facts
yeah,
are,
yeah, yeah,
right?
yeah.
Okay. So within facts, you're saying, okay, I can take features and I can sort of plus, because the features are different, or whatever the words are, you can
Yeah.
sort of compare.
Yeah.
So I have a question about feature reordering and the earlier observation that you said that 80% of the data are responsible for it.
Sure.
So are these critical features kind of identified after training, or do you have that information beforehand?
So there's lots of training jobs that are running through that, yeah, historically, and we kind of do offline analysis on that
importance.
data.
So you
So beforehand, right?
So you do feature importance analysis beforehand?
So it's more, everything is continuous, right? So for example, specifically what we'll do is we'll run an analytics job that analyzes the feature importance over the past 7 days of training jobs or past month of training jobs. We'll take that information and then in our data engineering job and our Spark jobs, when we generate these data sets, we'll plug that in. And for the next day of data that we generate, we'll reorder these features according to our past 7 days or past month of analysis. Yeah.
For the data you store, are you assuming the training job is like one kind of the training like model? Or it's just used by multiple different training models? Because the way you store it may hurt the other trainings, right?
Yeah, I mean, that's an excellent question. I can talk about a lot with that, lots of detail about that, but at a high level, each of these data sets roughly corresponds to one type of model, but there are different training jobs that are run for that model, which read different features. So for a given type of model, think a model that does Instagram, we're running hundreds of different training jobs doing hyperparameter tuning for that one model instance. And feature importance, which features we read, is one of those hyperparameters. And I totally agree where a certain reordering will not be perfect for all these jobs. And there's methods that we can do to improve overall the benefit. And that's a great point that you bring up. Happy to also talk about it. Yeah.
So when you do the training and before applying to feature reordering, what's the overhead of this reordering? I mean, how big is this?
Yeah,
What's the cost?
I mean, it's an additional, effectively a Spark job. So there is
So
overhead,
you
but
apply to all your files, just selectively some, or you actually apply?
I mean, again, this is kind of every day we're generating a new partition. When we generate that partition, we'll run a kind of a cluster by operation. Or sorry, not a cluster by, a reordering operation when we're generating that file. So there's kind of a bit of a,
And every time you observe like a lot of reordering in your experiments, or is it really very minor or sometimes?
well, the point I want to highlight here is that this is a one-time write. So, but there are thousands of training jobs doing reads.
Yes.
So the benefit overall for the training jobs is really just the one-time write is negligible compared to the benefit that we get.
Okay.
Yeah.
Quick question.
Yeah.
Do you assume it's hard disks, not SSDs?
These are hard disks, so Meta stores all these data sets on hard disks.
Okay.
My project that I quickly mentioned called Tectonic Shift was about how do we introduce SSDs to improve to not have to use a bunch of hard disks anymore. But in general, pretty much all the data at Meta is stored on hard disks
Okay, thank you.
in this Tectonic process.
Another question, this was done with a specific type of workload,
Yes.
Facebook,
Yes.
Meta,
Yes.
in mind, and heavily read-only kind of operations.
Yes.
And a very, I guess part of the whole thing is likes, posts, that sort of stuff. if I shifted it to another type of workload, how would that, what is
Okay,
your?
okay, yeah, my last piece is how do we generalize all of these optimizations or these efficiency optimization. They're not exactly the same because these are kind of tailored for recommendation, as you mentioned, but I'll talk about how we can kind of structure this. So next, let me quickly go through another example to really drill in this idea. As I mentioned, step one of this technique is really understand the application. And in reality, what these applications look like is kind of this, where each user will have multiple entries in these data sets associated with them. And this is because every time a user interacts, or sorry, requests an inference from this inference system, we generate a new training sample. So every time Alice browses a post on Instagram, we'll generate a new training sample corresponding to what specific item was recommended to Alice. The tricky thing here, or the phenomenon that arises here, is that the features inside this features column are only updated every time Alice interacts with one of these posts. So for example, if she doesn't like a new post, in between browsing all these different posts, this last inline post's value won't change at all. And so that leads us to our second step, which is to distill a system insight. And the insight here is that there's a lot of duplication inside these features for across the training samples associated with a given user. Almost 80 to 90% of bytes within Meta's recommendation data sets correspond to these duplicate or redundant values across these features. So what this means is, again, massive overheads across your entire pipeline spent managing redundant data. So obviously, the thing that we want to do is, okay, let's better encode or let's deduplicate this redundant data to get rid of these overheads. The challenge here is, well, these duplicate training samples from Alice are interspersed across billions of other samples from billions of other users inside these data sets. And if we try to do this in one component, for example, in the GPU, let's write a new GPU kernel that deduplicates these tensors, et cetera, well, the GPU only has a limited view of this entire data set, right? It only sees a few thousand samples. So there's not many duplicates there. And there's not much that the GPU or this optimization can do. So if we come back to this idea of end-to-end optimization, that is really what allows us to do this better encoding, this better deduplication. And so to start off, let's start in this data engineering layer, and let's cluster all of these duplicates together. So specifically, again, every time we generate a new training partition, every hour or every day, we'll run a clustering job over it to group together all of these duplicate features inside our data set. And what this means is that when we write to these columnar files, well, we get an immediate benefit here, which is that because they're compressed, by putting a lot of duplicates together inside these compression blocks, we just get immediate better compression, storage compression ratios. On top of this, when we read these mini batches during pre-processing, each mini batch is still compressed, meaning that we get better storage IOPS and network and pre-processing efficiency because, again, better compression ratios. But the real key benefit here is this idea of synergy. By grouping together all these duplicate samples into mini batches, we're able to leverage that in downstream components, right? Because now we have that entire view of duplicate data that we want to see. And I'll walk through what that means in a bit. In order to really leverage that and really to get that key benefit from deduplication, well, we have to address this next challenge, which is that tensors are not compressed like these columnar files. They're uncompressed data. And so, okay, to address this problem, let's introduce a new tensor encoding that can efficiently encode these duplicate samples. So as a bit of background, how PyTorch or TensorFlow represents these tensors for these tabular sparse features is in a keyed jagged tensor. And so each pre-processing worker will read, for example, this batch of data, and they'll convert it into this tensor format, which has two lists, a values list and an offsets list. And we'll encode this original mini batch like this. Each row in this mini batch will have an entry in the offsets list, and that offset will point to the values that row holds. And the point here is that you can see that there's a lot of duplicate values, 3, 4, 5 repeated many, many times in this values list, which again, because the GPU doesn't know that, the kind of structure of this data, it'll just repeat processing on all of these redundant values, wasting a lot of resources. So to address this problem, we introduced this inverse key-jagged tensor format, which now has this inverse lookup list, and each inverse lookup will now point to the offset for that inverse lookup, which will encode the values as before. So by adding this additional layer of indirection here, the synergy is that, the benefit is that we're able to reduce the number of values in this value system, really to bring it down and not have to repeat 3, 4, 5 many, many times. And that allows us to actually leverage this, technique on the GPUs themselves. And the last key optimization that we want to do is, okay, the GPU modules are not aware of this new encoding, so let's make them aware of how to use this new encoding. And so the last technique is deployed inside the GPU or the model architecture itself. As a very quick bit of background, we typically train these models using your typical data parallel and model parallel training. I won't go into the details here, but the point I want to make is that we have lots of GPUs that talk to each other for each training iteration that we send this batch through. So the last trick or the last technique here is that for each of these modules inside the model architecture that normally operated on a key-jagged tensor, let's just plug and play, kind of swap them out with a new module that does exactly the same thing, but is aware of how to read this new encoding, right? Work with this deduplicated encoding. And so I don't have time to get into all the details here, but the key benefit is that because there's fewer values here, there's less work that the GPU overall has to do in terms of network requirements, memory bandwidth requirements, and also compute requirements. So all of this combined together, again, is applying this idea of synergy, where by having these techniques work together, we're able to improve training throughput by 2.5 times, pre-processing throughput by up to 1.8 times, and storage efficiency by 3.7 times. And again, like with the ISCA work, all of these techniques are deployed at Meta's production fleets. Yeah.
So does reducing the randomness in input affect the convergence time of the ML model?
Yeah, that's a great question. So we actually see a benefit because for very kind of long tail features, by not having them kind of repeat over and over again, that allows us to not overfit the model to kind of these very rare features. So 2 points. First is that we don't change the semantics of this data. When I say deduplicate, the model still learns on exactly the same data. So if there are 3 rows that are duplicates, the model will still see that data 3 times. We just avoid repeating that work 3 times.
But earlier the data was kind of random.
Yeah, yeah, exactly. The only semantic thing that we change is clustering all these duplicates into one batch or a few batches. And as I said, that actually helps us improve convergence by a little bit because we overfit less, because very rare occurrences or very rare features are not repeated over and over again inside our data set. So it helps us not overfit the data. There's a bit more analysis in the paper on that, but at a high level, that's, yeah.
Do you have any analysis on the capacity grading aspect for changing this mini batch into a random, going from random samples spread across, all your mini batches to having many duplicate samples within a single mini batch?
But I think that was exactly the point I highlighted with the other question.
I think it's kind of like a follow-up on the previous one, where there is a change here that
Yeah.
happens in the optimization process in.
Sure, yeah.
Do you have any analysis on what actually happens when we have more?
Can you be a bit more specific about analysis?
Like guarantees that we converge to a similar.
We don't have necessarily theoretical guarantees. We've done kind of, regression testing on Meta's models, and we've seen, at least for their workloads, neutral or slight positive benefit, but I don't have formal guarantees on how that affects things.
Thank you.
So, okay, we're, I think, running a bit short on time, so let me quickly go through this last part, which is hopefully you've seen that applying all these optimizations is great, but doing so takes a lot of effort and as was mentioned, is very bespoke to these recommendation models, right? So instead of going through another example, let's talk about how we can automatically apply these optimizations across a very diverse set of ML pipelines. And this work will appear in the DLE standard here. So one option to efficiently process a lot of data is to use these traditional engines like Spark or Beam, Flink. And as I hinted at earlier, these engines are used in this training pipeline, specifically for this data engineering or offline ETL step. But for the online pre-processing step, we use other frameworks, typically like PyTorch data loaders or TensorFlow data. And this is because traditional data processing has distinct requirements from ML pre-processing. Traditional data processing, we really care about high throughput, massive parallels of getting results as fast as possible. And we're able to program these workloads using very structured interfaces like SQL. For ML pre-processing, if you've ever written a PyTorch data loader, you'll know that it's very ad hoc. You're writing very long Python scripts or even bash scripts, calling third-party libraries that you found somewhere online and working on very unstructured tensors. On top of this, as you'll see in a bit, there are very specific ML optimizations that have been applied to these ML pre-processing pipelines. And finally, in terms of resources, it's really about right sizing. As I mentioned at the beginning, we don't want to throw as much resources as we can because that doesn't improve your training throughput. We want to exactly use the right amount of resources to meet the demands of your training job while performing this pre-processing, but no more than that. Okay. So if we want to build a very general purpose, efficient framework to do all this ML pre-processing, what do we need to do? Well, first, we need this similar, easy to use interface, but we want this interface to capture the semantics or the intent of what each pipeline wants to accomplish. This is important because when we apply these efficiency optimizations, we want to ensure that they are still correct. They still generate correct outputs. And finally, as I mentioned, it's all about right sizing the resources that we allocate to the unique demands of each training job. So this is difficult because doing this introduces a lot of complex systems decisions. So if we have a very simple pipeline that takes an image, blurs it, crops it, there's lots of different ways that we can do this. For example, in this work, we introduced this optimization called a semantic preserving reorder, which if we have this pipeline, well, we can execute it multiple ways. We can first blur that image and then crop it, or we can crop the image and then blur it. And why does this matter? Well, the option on the right uses much less compute because we perform this expensive blur operation over a much smaller cropped image, right? And so this is great in this case, but there's two problems here. First, how do we know when this general reordering is allowed according to the semantics or intent of the pipeline? And secondly, how does this interact with other optimizations? So an obvious optimization that I'm sure everyone has heard of is caching, right? Let's take this pipeline, materialize or cache its output, and reuse it every epoch. But let's just assume that we know that this crop operator is a random operator. So we can't actually cache this output because caching a random operator will destroy semantics and affect your training convergence, right? So what we can do instead is let's blur the image first, cache it, and then on the fly every epoch, let's do this crop dynamically. So we still get that randomness in our pipe. This introduces a few challenges, as you can see, because, well, the version on the left is more compute efficient, as we saw in the previous slide, where we do this crop first. But the version on the right is more cacheable, right? Because we cache this very expensive blur operator. So there's no one right answer here. The execution plan that is best really depends on all these different factors. Your training throughput demands, what hardware resources you're using, the kind of dynamics of all these different operators. And to complicate this even a bit more, there's lots of other optimizations that we can apply to this pipeline. For example, we can take all these different operators and execute it in different backends. We can use the training nodes host CPU, distributed preprocessing service like TPP, or even design a new accelerator for it. We can fuse the operators together to avoid transferring data between them. We can prefetch this to overlap processing with training. The long story short is that combining all these optimizations together introduces this massive design space that we have to reason through. So to address this problem, we built Cedar. Oh, it says Cedar there, which is this framework that allows users to define these high-level data pipelines. And the goal of Cedar is to perform this data pre-processing fast enough to meet the demands of your training job, to generate these tensors fast enough for your accelerators, using the least amount of resources possible. So to do this, we have 3 components. First, we provide users with a composable API to build these pipelines. Then we'll apply static optimization passes to that pipeline to improve its efficiency. And then during runtime, because we have to right-size resources, we'll take that optimized plan and then allocate resources dynamically to it in order to meet the demands of your GPU. And let me quickly go through each of these components one by one. So first, as I mentioned, we have this kind of Pythonic declarative programming interface. And I just quickly want to highlight one thing here, which is that we're able to use this to capture semantics from the user in 2 ways. First, users are able to specify dependencies between operators, so kind of it depends on relationship, that prevents us from doing reorderings that would violate this dependency constraint. So they're able to overlay kind of a dependency graph on top of their pipeline. Secondly, they're able to label random operators, which will prevent us from caching after them. So given this pipeline, our next step is to apply these static optimization paths, and we'll do so through a series of steps. First, we'll take a specific optimization technique, for example, reordering here, and we'll enumerate all the different execution plans that we can generate that are permissible by applying this optimization technique here. So not violating that depends on relationship. Then we'll use a cost model to estimate the cost of each plan in terms of how efficient that plan is. Don't have time to go into the details here, but of course, happy to talk about any of this. And then using this cost model to estimate the cost of each plan, we'll prune away or get rid of the very inefficient or very expensive plans and keep the very efficient plans. And then we'll kind of repeat this process iteratively by taking the efficient plans and enumerating new plans using additional optimization techniques like caching. So what we end up with here is this very optimized execution plan. And now during runtime, when the training job starts, we'll begin by deploying this plan. And the goal of our runtime is to really right-size the parallelism of resources that we allocate to meet the demands of your training job. And we do this by effectively using back pressure, but what that means is we'll insert these buffers throughout this entire execution plan, and we'll scale parallelism based on the length of those buffers. So if there's very high bandwidth demands, we'll see low buffers, short buffers, and we'll scale up resources allocated to processing. If we have low bandwidth demands, these buffers will fill up really quickly, and we'll see large buffers, so we'll scale down the amount of resources that we allocate. And one important thing I want to note here is that if Cedar deems that it's more beneficial to only use the training nodes CPU, so not have any distributed resources, we're able to dynamically detect that and make that swap and kind of compress or coalesce everything onto the training nodes host CPU. For example, there are very low bandwidth demands. So to show that all these techniques result in Cedar meeting this goal of high training throughput using the least amount of resources, I want to quickly walk through two results. First, can these static optimizations maximize the efficiency of this plan in terms of the amount of throughput that each plan achieves given a fixed amount of resources? And then can Cedar dynamically scale these resources to meet the demands of the first set of training jobs? So first, let me start with the static optimizations. And specifically, we compared Cedar against several state-of-the-art ML preprocessing frameworks like PyTorch data loaders, TensorFlow data, FastFlow, etc. And for each of these systems, we have two deployment scenarios. A local scenario where each system is able to use only the training node's host CPU to perform processing. And also a remote scenario where these systems, if they're able to, are able to offload processing to a remote service like DBP and scale it up to offload some of the pre-processing that it's performing. So I'll show you in a bit more pipelines, but we ran across a diverse set of ML domains, in this case, computer vision. And for each of these domains, we have a few different frameworks that we're using. For example, a PyTorch version and a TensorFlow version. So in other words, we're using PyTorch to build this pipeline and TensorFlow to build this other version of the pipeline. And this is important because some systems like TensorFlow data aren't cross-compatible because TF data uses TensorFlow under the hood. It's not able to support PyTorch pipelines, for example. And so, like I mentioned, we ran all of these experiments across a diverse set of domains, from computer vision to NLP to speech. And long story short is that Cedar is able to support all of these different diverse ML domains and also these diverse ML frameworks. And on top of this, by combining all of these optimizations together, Cedar is able to improve efficiency by up to 1.8 to 10.6 times compared to these baselines. So next, let me show you if we're able to scale our resources allocated to the demands of the training jobs. And how to read this graph is as follows. We took the CV torch pipeline, and Cedar decides to optimize that pipeline by offloading some of the processing to a remote or distributed resource. What the blue line shows is as we increase the parallelism, the amount of processes allocated inside that resource, the throughput in terms of samples per second that Cedar's execution can achieve. Then each horizontal line shown here represents a different target training throughput that we set. So for example, this line here shows that we simulated a training job, which requires 600 samples per second to keep up to make sure that we're not stalling the GPUs. We did five different target throughputs. Then the vertical line shows the auto-tune or auto-scale parallelism that Cedar converges to for each of these targets. So what we want to see here, and what we do see, is that the intersection of the horizontal and vertical line is just below the blue line. Because what that means is that the throughput that Cedar is able to achieve, the blue line, is just above the throughput demand of your training job, right? And on top of this, it's not all the way up here, right? We're not using extra resources that we don't need to perform this processing. And quickly, I want to highlight that, as I mentioned before, when we have very low throughput demands, when there's no need for disaggregation for scale out, then Cedar is able to observe that and not use any distributed resources necessarily. So I have a few minutes to talk about future work, but before that, super quick questions.
Going to slides, but what happened with the NLP benchmark?
Yeah. In what sense? Some of these are lower.
But the
If that's what you
NLP
mean.
seems to be kind of sticking out, right? Any insights there? The right
So this point or this
one over. NLP, there you go, NLP, yeah.
this
On the
point,
left side, the local.
this point. So Cedar is a bit lower than TensorFlow here. So this line is TensorFlow because it's so Cedar adds a bit of overhead for tracing through each sample to make sure that it's resilient. So if things crash, we add a bit of logging overhead to each training sample that we process. So long story short, there's a little bit of overhead for each sample that we generate. And because NLP data sets are very small compared to like an entire image, that overhead is a bit higher for us. Yeah.
You also have overview for cost-based optimization that you're doing, right? You're enumerating. Is that enumeration space large, but what are you using for optimization there? Is it a greedy algorithm of some sort, or what is that?
Yeah, so, the overhead, I'll answer your question in a second, but, the overhead, the good thing about these training jobs is that we can amortize that over, hours or days long training jobs. So as long as the optimization takes a few minutes or under a few minutes, which it does, then we're able to, that's completely negligible compared to the 2-day long training job, for example. Kind of the optimization step that we use back here is kind of this variance on what branch and balance. We enumerate a bunch of plans using a system optimization, we print it down, enumerate more plans, print it down, using this cost model.
Okay, and that's true for dynamic or static, or is that?
Sorry, we only do this offline kind of static optimization. Dynamic, we just,
Adjustments. so
we,
random
yeah,
adjustments.
we use kind of a tail lighting algorithm. Yeah,
When you add these, let's call them pragmas to the PyTorch code, like dependencies
Mhm.
or other things, so that makes it very dependent on user being capable of doing it well. So how much effect, did you notice anything, or were you the coder of this who understands everything?
yeah, so I mean, we do assume that. So these are kind of black box PDFs, and there's other ways of distilling these dependencies, like kind of code tracing and more static analysis, but we really just rely on the expertise of users because these could be very diverse pipelines from recommendation to vision to NLP. And it's very difficult for a system to understand what are the semantic, like what is semantically correct in pipeline. So we do kind of require. But I think the benefit with Cedar is that the kind of framework that we provide, we have a bunch of composable modules that you can stitch together. So for example, we have a crop operator that it's one line of code that goes to a blur operator, that's one line of code. So instead of having to write a new function every time, users are hopefully able to overall have less work that they do because the interface is much smaller, at least in our opinion. So quickly, let me spend about 2 to 3 minutes. I know we're kind of out of time to highlight what I think is really exciting going forward. I think that there's still so many opportunities when we think about how to build systems for the entire ML pipeline across each of these areas, ML data systems, serving systems, and the underlying hardware and software infrastructure. I'll highlight some exciting opportunities in each of these. So first, I talked a lot about building efficient data systems, which is efficient is hidden there. And there's still a lot of opportunities here going forward. For example, there's decades of traditional data systems research, and we really need to understand how we can bring all these techniques into the ML pre-processing space. But at the same time, hopefully you've seen in this talk, there's a lot of unique optimizations that we can apply to these ML data systems and a lot more to be uncovered here. And finally, I think that ML data systems is a rich area where new hardware accelerators can really make an impact beyond just simply continuing to accelerate these really dense matrix multiplies that we're heavily focused on. I also think it's important to build useful ML data systems. And this is really timely because we've seen this recent shift to data-centric ML, meaning data scientists and data engineers are exploring algorithms that improve how we use the data as opposed to how the model architecture themselves. For example, data selection, feature augmentation, or data augmentation, dealing with data drift, et cetera. But there's this big gap here in terms of building systems that not only provide data scientists with the necessary information to explore these algorithms, but also allow them to deploy these mechanisms into an actual system at scale. I think that Cedar is uniquely positioned as a platform to explore all of these different ideas on top of. On the inference front, we've seen a lot of focus on these generative applications recently, and specifically these compound systems that don't just have one LLM inside of them, but an LLM or multiple LLMs that interact with different components like agents or tools or retrieval. I plan to build frameworks to serve these applications by not optimizing for just one narrow component, but performance of a single element call, but instead focusing on the entire pipeline. And I think this is a promising approach because with my previous work on the original Llama, we built a serving framework for these compound video analytics pipelines, which similarly have multiple interacting components, multiple interacting models. And the takeaway from this work that we learned was exactly the same. We don't want to over-index on optimizing a single component, but really understand the overall application performance as a whole. And finally, I plan to build infrastructure that's not only scalable, but also secure. And this is really timely because recent work has shown that the interactions between different components when we deploy these LLM models or other types of models into the real world introduce vulnerabilities that can compromise user data and privacy. And to address this, we obviously first need to understand these interactions better in this new class of compound systems. And once we understand these vulnerabilities, then I plan to build hardware and software infrastructure to better ensure data security and privacy throughout the entire pipeline. And I'll do this by formalizing interactions between these components, between these systems, and then deploying full stack hardware and software solutions. For example, with my work on previous work on building secure cloud accelerators throughout the entire pipeline. So to wrap up, I just want to highlight 3 important points throughout this talk. First, modern ML deployments are much more than a bunch of accelerators. They're pipelines with many diverse, complex, scalable interacting systems. To continue scaling our ML capabilities, we need to focus on improving all of these components to end. In this talk, I've shown how my work achieves this by building scalable, efficient, and easy to use ML data systems to handle the massive data demands of modern training jobs. But there's still so many more exciting research opportunities to continue going forward to improve ML systems, from the training and inference pipeline to hardware and software infrastructure. And all of this, again, is possible when we start thinking outside the confines of the GPU and look at the entire pipeline. Thank you so much for your time. Happy to take any more questions.
Yeah, so,
Sorry for moving over.
interesting talk. So, I guess one question is your future work, which is
Yeah.
towards inference pipelines as compared to, I guess that's something you mentioned, as
Sure.
compared to as training pipelines. Can you see immediately 1 or 2 opportunities for optimization that did not exist in training pipelines, which are, let's say, training pipelines versus inference pipelines? What will be different?
So inference pipelines are very kind of latency constrained, and especially when we think about how these inference pipelines or compound systems are deployed today, our phones and our laptops everywhere, they're very resource constrained as well. So the key question here is how do we take massive models, multiple models, which need a lot of resources for model weights, AV cache, adapters, etc., and execute all of these different components in the very resource constrained environments.
Yeah,
So that's, yeah.
So I'm not headed towards more challenges, that's fine. There'll be more
Okay.
different challenges, right?
Sure.
But are there more opportunities? For optimizing, like you identified 5,
Oh,
6
sure.
different opportunities in the context of training your pipelines or whatever it was. In the context of inference pipelines, are there more things which are not feasible possibly in the other one as optimizations?
Yeah,
Have you thought of that direction?
I think, to answer that, how hopefully you see my approach is really taking application, analyzing and understanding its requirements, and then mapping that down to optimization and frameworks to improve them. And so to answer your question, I think it will be heavily dependent on what the application is. Something for an IoT device looks very different from kind of a cloud scale data center. And so I think the opportunity here is really, well, one opportunity that I mentioned in that example, that resource constrained environment. So with the resource allocation scheduling looks very different from kind of the resource allocation scheduling that we talk about with Sphere. But again, kind of, we need to be cognizant of the application and how that drives these operations.
Any other questions?
Back to the serial work. Yeah, so I wonder what is the executable model of this niche? Like, do each operator has to finish first for the next operator?
Oh, it's all asynchronous. So having buffers in between them allows us to kind of make everything asynchronous.
So are they doing pipelining in between?
Yeah.
But you also mentioned like, some operators, they run on different data systems. So,
Yeah, so everything, so for example, if we have like an operator running on the local training nodes with CPU, and an operator running in DVP, for example, they kind of run concurrently at the same time. And all these operators care about is just filling up the buffer. Like everything kind of runs asynchronously, everything kind of overlaps with each other, pipelines with each other.
so, is there any cases where you would need to materialize the data task operators?
For the pipe, maybe your question is if there's any like kind of joins or aggregations or kind of cross sample operations that need to happen here. For the pipelines that we looked at, no, everything is just sample by sample. But that brings up a really interesting point. There are some cases where you can think of that require more aggregation, for example, collecting statistics about a data set before normalizing it, for example. And so I think that presents different set of challenges that we need to address.
So you mean like in the operators for this legal system in at Meta, like most of the operators, they're pipeline, they're not blocking. So we're saying.
For the last mile pre-processing bit. I also want to note that we use, like, as I mentioned, there's a bunch of offline TL that is kind of a batch job.
Thank you.
Yeah.
Anything else? Okay, Manny.
I can ask you.
Okay.
So you look at environments where we're very data rich,
Yes.
right? There's lots of data and you want to sift stuff out of this data. There are lots of situations where you want to do this kind of training, but you're data poor. Right? How would you think, and you want to do it at scale, and I can think of, I work in the area of smart cities, I can think of lots of applications where I don't have data as to how large systems are going to behave in an earthquake, for example. But I want to generate data. And so that's another knob in this whole process as to how much data can I use?
Yep.
Have you thought about that? Here you've got.
Yeah. So there's two answers that I'll give you here, which I think are really two exciting different directions. First is, again, this idea of data-centric ML, where if we're data poor, for example, some people are saying like we're running out of internet training data, right? Data augmentation, synthetic data is a really rich opportunity to go forward in these environments. We don't have the systems to work on these at scale. And so how do we take maybe a data generation or synthetic data generation algorithm, understand what that algorithm needs from the current data that we have, but also take that algorithm, plug it into this really scalable data pipeline and have it, generate data for these training jobs. I think that's one really exciting area. And secondly, as I mentioned before, being application driven. For example, with the recommendation models where we have all this data, that's one application, but there's, in biology, ecology, all these different domains which are working with lots of data. I think the optimizations that we'll see there might look a little different, but the kind of core technique of, hey, understanding the application, seeing how we build a data system for that, and then building kind of a framework that supports all these different domains and environments is going to be a lot of interesting paths for each of these kind of tasks and applications.
Any other questions, folks? Okay, let's thank you all.
The setting from that. It's not.
Yeah, we can do
She
that.
tried for 10 minutes.
I have to run to class right
He's a hardware guy.
now.
I'm always. Let's.